Okay, so last topic in this unit, projectile motion. It's going to use everything in this unit except graphing. So there's some vector component stuff, there's some acceleration stuff, there's some v equals d over t stuff, okay? It literally is everything but graphing, all being used in one type of question. So, should you be pretty much guaranteed that there will be at least one of these on your unit exam?
Yes.
Yeah, because it allows me to test everything except graphing in one question. Okay, yeah, absolutely, I would do that because it means I don't have to have as many questions on the test. Okay, so certainly what we're going over today is a big part of this unit. All right, so first off, the definition of a projectile. Okay, a projectile is any object in unpowered flight in the Earth's gravitational field. Okay, that is as simple as if you drop something. Okay, if you drop something, it is an unpowered flight while it falls. Okay, it's like Toy Story. Okay, it's not flying, it's falling with style. Okay, well, it's exactly the same thing. A projectile is any object that is essentially flying, falling through the Earth's atmosphere, only powered by gravity. Okay, so a plane is not a projectile, it's powered. Okay, a rocket is not a projectile, it's powered. Right? Anything that has an engine that is producing propulsion or thrust is not a projectile. Everybody all right with that idea? Okay. Projectiles usually have two dimensions to their motion. Sorry.
What about a kite?
A kite is not, because it is using the wind to create lift. That's a good question. So, it usually has two dimensions. The only time that a projectile doesn't have two dimensions to its motion is if it is either thrown vertically straight upward or dropped, so that it only moves vertically, right? The projectiles we're going to deal with, they are going to have two dimensions to their motion. So that means that they are moving both horizontally and vertically at the same time. Kind of like the boat questions we get. Okay? They are two types of motion occurring simultaneously. Right? The vertical component, or the vertical dimension to any projectile's motion is accelerated motion because of gravity. Okay? And it's horizontal. We're going to assume we're working in the perfect physical world where there's no air resistance or anything like that. Okay? That will move at a constant velocity. Okay? Now, projectiles are actually a big part of kind of our experience. We just intuitively understand how projectile motion works. Like, for example, when you were a kid and you were maybe trying to spray your friends or your little brother or sister with the hose in the backyard, okay? If they went like a little further away so that they were out of range, could you still get them?
Just angle up.
Just angle up, exactly, because we have this intuitive understanding of projectile motion. Every single water molecule that comes out of that hose is a projectile. Okay? And if you change the angle at which they come out of the hose, they'll go farther. It's not because they're coming out of the hose any faster. You've just given them more time in the air by changing the angle at which they leave. So they're naturally going to travel farther because they have more time in the air to do so. Okay? If you want to throw a ball to somebody else, okay, you don't throw it on a straight line. If you do, what will happen? It'll fall. Yeah, it'll fall to the ground long before it gets to them. Okay? Those Hail Mary passes at the end of a football game are always a big rainbow. Okay? Because, well, they got to go a long way. Right? So we naturally have to aim them upwards in order to get them there. All right, here's a question for you. I have two bullets. One is in a rifle, and the other is just being held. Okay? So the situation is that I've got one in the rifle with my finger on the trigger, not pointed at anybody, okay? And I've got another bullet at exactly the same height above the ground that I'm just holding, okay? I'm going to pull the trigger and let go of the bullet at the same time. Which one hits the ground first? Both. They will both hit the ground at the same time, okay? Why? Because one is going to do this, the one that was fired from the gun is going to do this, and the one I drop is going to do this. Do they both fall the same distance? And It takes them the same amount of time to do it.
Presuming
I'm not saying they hit the same spot. They absolutely do not. But they do hit the ground at the same time because both of them have an initial vertical velocity of 0. They both are going to accelerate at negative 9.81 meters per second squared. And they are both going to fall the same distance. Okay, whatever it is, whatever height I was holding it at. Let's just say it was 1.5 meters. Okay, well, if they both share that information, how can their time to fall to the ground be any different? The answer is it can't. Okay, Mythbusters actually did this years back, okay, where they tested this and absolutely 100% true. Okay, even in the non-perfect, real physical world, okay, they still both hit the ground at the same time. Because they both fall at the same rate. I don't have it actually. Okay, I have some other Mythbusters ones. We're gonna watch a lot of videos over the next couple of days. Okay, but I don't have that. So it's disappointing. But I have the one where they do the water slide one, which is really cool. So does that sort of make sense to everybody? Okay. So if I'm looking at projectiles, both of these are projectiles. They both fall the same distance. Their vertical dimensions or their vertical components are the same. Obviously, their horizontal components are different. Right? Let me propose another situation for you. Back in the late 90s, Lexus came out with their newest sports sedan, Lexus IS 350, I think it was. Okay? And they had this advertisement. Okay? So here's the situation. A car is being held by a helicopter 4,000 meters, or sorry, 4,000 feet above a spot on the ground. An identical car, a Lexus IS 350, okay, is over here. They're going to race to the X. Who's going to get there first?
One being dropped.
Okay. One being dropped. Okay. They have to go the same distance, right? Okay, and this is happening in the real physical world, not the perfect physical world. So the Lexus's ad campaign went like this: the Lexus IS 350, faster than gravity.
There's no way, because you have to account for the time to accelerate and the friction that is lost.
But the
So
same
it was
thing-
accelerating at faster than that, but you want like meters per second.
That's what they want you to think. This is about how people trick you in an advertisement. Okay? I'm going to show you the ad. It is damn impressive, actually. Okay? The ad looks really impressive if you don't think about it. Okay? There's little things to watch for. Okay? We'll see if you guys notice where they trick you.
Do they use mass?
What was the trick in the video?
They drop the car later.
Yeah, they still covered the same distance. It was still 4,000 feet for both of them. But the car on the ground didn't start from rest. Okay? It's not that I mean, that car is powerful, it's fast, but it got a head start. It was moving at its top speed when they dropped the car. When did the dropped car start from?
Zero.
Right, and when something falls in the Earth's atmosphere, does it accelerate all the way to the ground? No, it reaches terminal velocity. Okay, the speed at which you cannot fall any faster because the force of air resistance acting up is equal to the force of gravity acting down, and you stop accelerating. That speed is about 120 kilometers an hour. Can a car on the ground go faster than that?
Yeah.
Absolutely. That car being dropped had no chance of getting there first, but it sounded impressive because what did people visualize? They saw that car on the ground start from rest. What they don't make note of is the fact that the car is dropped after that. Okay? They edit out the portion of the driving of that ground car where it accelerates from 0 to its top speed. It was on an airport runway. Okay? It had all kinds of time to get up to speed. Okay? It looks impressive because most people don't think about it. right? They have this gut reaction. Gravity's fast. I don't want to fall. I'm afraid of falling because when you fall, there's a sudden stop at the end where you're going really fast, and that's bad. They play on that because they play on it because most people don't understand projectile motion. They don't understand the physics of what just happened there. A car on the ground gets to move in its most aerodynamic dimension under constant power. The car falling can only fall, or only accelerate at least, until it reaches its terminal velocity. And on top of that, they crippled the falling car. They weighted it so that it fell flat. Okay? You drop a normal car from a helicopter, and the first thing it does is nose down and fall in its most aerodynamic dimension. Go way faster. Terminal velocity is a lot faster. Okay? Because it's falling in its most aerodynamic dimension. It's still going to have a terminal velocity, but it'd be faster. Okay? So they weighted it so that it fell flat. Okay? That was actually the biggest challenge Mythbusters had when they busted this, was they had to figure out how to weight the car so that it would actually fall like this, because every car they dropped just nose down right away.
They were just dropping cars.
Oh yeah,
They
I'm going
had
to show you the
money
video.
to drop cars.
Yeah. Yeah, let me show you
They're
the video.
rich YouTubers,
It's great.
of course.
So, can advertising be misleading?
Yes.
Absolutely. Okay? When you first saw that ad, it seemed pretty impressive, right? The car on the ground made it there first. It's possible to set it up every time that way. Okay? You just have to make sure that you set the distance right for the maximum speed of that very fast car. Okay, so that's the simplest kind of projectile. It's just falling.
Would it, like, would the weight affect the falling object?
No, because all things, regardless of their mass, fall at the same rate. Yeah, in a perfect physical world, right? Obviously, in the real world, there's air resistance and things like that. So if I drop a bowling ball on a feather, well, a feather is designed to catch air. It evolved to do that, so it goes like this when you drop it. If you drop it in a vacuum, it just falls back.
Say if you
I have a
drop-
video of that. Video of that?
I've seen that video, I think.
The Brian Cox one?
I
The
don't.
big vacuum chamber.
Big vacuum chamber, yeah.
I don't remember where I saw it.
So, that's for falling objects, simplest projectile, okay? The next type of projectile is one that's going to have two dimensions to its motion, okay? So if I'm looking at something moving horizontally, like if somebody runs off a cliff, or somebody shoots a gun horizontally, or shoots a bow and arrow, okay, horizontally, okay? The path of the object is like this, okay? It's always going to arc down to the earth. We call that a projectile arc. So, if somebody drives off of a cliff, okay, not that they would, okay, I'm not saying they would, but if they did, okay, when that arc starts to happen, okay, it's like at first it's mostly horizontal, but it very quickly becomes mostly vertical, right? And the reason for that isn't that it's no longer moving horizontally. It's moving horizontally at a constant velocity the entire time, all the way to the ground, okay? But the difference is that it's accelerating downward, so it starts moving a lot faster downwards than it is horizontally, and so the downward part becomes the dominant part of that motion. So it looks like it's all vertical, but it's not. It's still moving horizontally the entire time. Okay, so if you've ever like run off a diving board, like the 10-meter diving platform, okay, like you can run off, but you're never going to hit like you're never going to miss the water. Okay? The vertical part of your motion is still going to be the dominant part, even if you're really fast. Okay, it doesn't matter how fast you run off of there. They've designed the pool, hopefully, okay, so that you can't, okay, possibly go too far. Right? It's always going to become the dominant part. Okay, so got a car off a cliff. Examples of how a question like this, like the car going off the cliff, would work. So let's say I want to figure out how far from the bottom of the cliff the cars are going to hit the ground. Okay? So in order to do that, I would have to know a couple of things. I would have to know how fast they're moving when they drive off. Okay? They've been accelerating. They were older cars, but they've been accelerating a bit. Let's say that probably by that point they were moving at about 25 meters per second. Okay? And remember, what I'm trying to figure out is this distance here. Okay? Now, other things I would know. I would probably know the height of the cliff, which would be my vertical displacement. That cliff looked pretty tall. I'm going to say the cliff was 80 meters. Okay? What else do I know?
Gravity.
Okay, and I'm going to make these both positive since the only direction they move is down. They don't move up. Okay, so I'm just going to say that down is positive because this was down and this is down. Okay, anything else I know?
The initial vertical velocity.
Exactly. This is where we have to break this up into both vertical and horizontal parts. Okay, the only thing the vertical part and the horizontal part share is time, just like the boat questions. Okay, the only thing they shared was time. Other than that, they were independent of each other. Okay, so I know from a horizontal perspective that the car drives off the cliff at 25 meters per second. I'm trying to figure out how far it goes or what its displacement from the bottom of the cliff would be. Since I know that it's moving at a constant velocity, I know I would use v equals d over t to do any calculating with it. Okay? Horizontally, the object travels at a constant velocity, so I always use v equals d over t. Vertically, it's always accelerated motion. Right? So I need the time if I'm going to calculate d. Can I get it from my vertical information? Yes. This is how most projectile problems work. You either have to use the horizontal information to get something for the vertical, usually time, or you have to use the vertical to get something for the horizontal, usually time, because it's the only thing they share. Does that sort of make sense? All right. So I need the time. What formula has those four things in it?
Isn't it like v d equals vit plus 1/2 dt squared?
Yep. You know, that one I told you didn't have to use to solve for time unless,
vi.
which it is. Okay, so I can solve for time. Okay, and so that's going to mean d over 1/2 of a square rooted equals t. So for this one, that's going to be 80 divided by 1/2 times 9.81. I said I'm going to make them both positive because they're both down in this situation. Okay. All right. So let's say we've got square root of 80 divided by 4.905. That's half of 9.81. I'm just doing that in my head. Okay. All right. So the cars fall for 4 seconds. That might not have been 80 meters. It was a long time that they fell for, but I don't know if it was 4 seconds. But okay, let's say it was 4 seconds. So now I know the time, 4.0 seconds, and I'll keep all the decimals as I go through. So now I can calculate how far from the base of the cliff they land. Okay, well, it's going to be 100 meters. Okay, just over 100 meters. Okay, so times 25. 100, well, I only have 2 significant digits, so 100. 1.0 times 10 to the 2 meters would be the distance from the base of the cliff. Okay, everybody all right with that? You don't want to be in that car. Okay, definitely no. All right, would the same be true if, let's say I had a plane flying over, let's say like a bomber flying along and it drops a bomb? Would that be the same kind of situation as this?
Yes.
Yeah. Okay, so the initial vertical velocity of the bomb would be 0. Okay, but the horizontal would be a lot, whatever the plane was moving at, right? Because once you drop it, okay, like they would actually move together like this, okay, as they go. It's actually why when a bomber drops its load, it needs to go, it needs to bank and turn, because you don't want to be over top of the explosion, right? Which is what would happen, okay, unless you were to change your speed.
When you say the initial velocity of the bomb is 0, what would be the velocity of the plane?
The horizontal is the velocity of the plane, yes. The vertical velocity is 0, because a bomber is going to fly straight and level when it's going to drop, right? That way that's the most accurate way for it to deliver its payload, Okay, so on that. Next. Okay, so different question, same context. So, bomb is dropped from the plane, right? So the plane is here, okay? Bomb is going to fall along this path. This time, I want to calculate the height from which the bomb was dropped. Okay, so we'll say that the plane was moving at 200 meters per second. Okay, we'll say that the distance horizontally that Major Kong and the bomb travel is, let's say, 800 meters horizontally. Okay, and we want to calculate the height it was dropped from. Okay, so with any projectile motion problem, the first thing you need to do is write your givens split up into the vertical and horizontal components. Whoop, that's not a Z, that's a 3. Okay, so horizontally, I know that the speed or the velocity is 200 meters per second, and I know the distance is 800 meters. Okay, I guess that'll work. Okay, so what do I know vertically?
VI is 0.
VI is 0. What else do I know?
Acceleration is 9.8 meters per second.
And I'm looking for the vertical displacement. I'm looking for the altitude of the bomber. Okay? From watching the video clip, it didn't look like it was very far off the ground. Okay? It was basically like, you know, terrain hugging, okay, all the way along. So this is probably not going to be a really large altitude that it's dropped from. If I want to find vertical displacement and I have VI and A, what don't I have? Time. Okay, so I need the time. Can I get it with my horizontal information?
Yep.
Okay. So, time to the ground, 4 seconds. So it wasn't 8 seconds. So I guess, you know, if you're riding a bull or horse, you've got to be 8 seconds in the rodeo, right? Yeah. Okay. All right. So only 4 seconds. Now I can bring that over here. The only thing that I can bring across from horizontal to vertical is the time, because when the time is up, both things stop. Okay. So now I can calculate D. So I'll go back to D equals VI times T plus 1/2 AT squared, okay, knowing that VI is 0. Right? All I have to do is plug in my numbers now. So 1/2 times 9.81 times 4 squared. Okay, they were only 78 meters off the ground. Now, it didn't look like they were very high. I mean, when they were going towards those ICBMs on the ground, it looked like they could have just about scraped the bottom of the plane with them. Right? And again, I picked these numbers like totally out of my head, so stuff like that will happen sometimes when I do that. All right, so that's another type or another way that a horizontally projected projectile question could go. All right. Now, the next one is still a horizontally projected projectile. Does anyone still need this? Okay. So now, let's say, anyone seen the movie Thelma and Louise?
These are all old movies.
I know they're old movies, yeah. Don't watch Thelma and Louise. 2 hours of your life, never get back. Okay? Terrible movie. Right?
Some movies
At
are
the
good.
end, when they drive off the cliff, spoiler alert,
Oh.
like you'll cheer because you'll know the movie's over. Okay, yeah. All right, so car drives off a cliff at an unknown velocity. Okay, cliff is 200 meters tall. Obviously, acceleration is 9.81 meters per second squared. VI is 0. Okay, and they hit the ground. "65 meters from the base of the cliff." Calculate the speed they drove off at. I'll give you guys some time to try that one on your own. Time, yeah, I got to use the vertical information to get time, okay, which will be our d over half of a square rooted to get t, right? So that's going to mean 200 meters divided by 1/2 times 9.81 square rooted. All right, so they're going to fall for 6.39 seconds. All right, well then I can bring that over here, 6.39 seconds. I also know the horizontal displacement is 65 meters. Okay, so now I can figure out what their horizontal velocity was. So I take my 65 and I divide it by this number here. Okay, and it's going to be that they were only moving at 10 meters per second, which is not very fast. And that's what happens when Coder picks numbers out of his head. Okay, sometimes the answers are not really sensical. All right, everybody okay with that one? Yes. Okay, so those are horizontally projected projectiles. Okay, the same would be true if you were like, I don't know, like if something just ran off, like rolled off a table or something like that. Okay, so any of those types of questions where you know there's no vertical component at the start. Okay, the object is not moving vertically at the beginning, then it is a horizontally projected projectile. Okay, now we haven't really brought a lot of vector stuff in with these because we don't have to. Right? But what comes in when we start dealing with the vertical ones is something like this. Okay. Now, I just groaned, but like, it's not as bad as it looks.
Looks pretty bad.
Well, no, it's just because I drew the whole water slide.
Oh,
Okay.
everyone's with the end.
Yeah, we're only dealing with the end.
Oh.
Okay, this part here where they're launched off the end of the water slide.
So we don't even have to touch or pay attention to your.
To this part, no. This is to go along with the video I'm about to show you.
Oh, okay.
Because this today is about watching lots of videos. Okay, and so like tomorrow, we're gonna get into when movies do bad physics. Because there's a lot of that. Okay, and there has been since CG became a thing. Because before CG, you legit had to do everything. Okay, if you wanted to film a car, have a shot of a car jumping over something, you had to jump a car over something. Okay, that means you had to plan it out, you had to build the ramp, you needed to put the cameras in the right positions and all that kind of stuff. Now you just go, hey, computer guy, make that look good. Okay, and they don't have to do anything. They don't have to. They can just fake it all. Okay, I mean, my gosh, they can fake entire people. Yeah, they can totally do that now. Okay, I don't know if you guys have watched any of like The Mandalorian. Luke Skywalker looked freaking awesome. Okay, they can do that. They can just totally fake people. Okay, well, they can totally fake anything now because if you have a computer, you can make it happen. Just sometimes they don't do it very well, and then it looks dumb. That's the trick. Right, is if you do a good job of it, nobody will ever know you CG'd it. But if you try to do something like super spectacular, it sometimes, well, ruins the most important part of a movie, the suspension of disbelief. Okay, you can have an enjoyable experience at the movies as long as your disbelief is suspended. Okay, it's one of the key elements of good movie making. If you do a bad job of something, your disbelief is no longer suspended and you're disappointed by the movie. Okay? And yeah, or what's that?
It says every movie ever.
Yes, many. There's some that do a pretty good job. Okay, a lot of modern science fiction movies actually do a really good job of trying to obey the way physics would work. Okay? And if they don't, they still make it look at least somewhat believable. Okay? And then there's other movies that are just outright trying to look cool and fake.
Well, but the problem with movies is they spend about an hour building the plot, and then you get about half an hour worth of action, and then the movie's over.
You gotta watch different movies. Okay.
No, because then they're all the same though. They're all like, oh yeah.
Here's how a question like that one is gonna work. Okay? What we would need to do if we wanted to, do this for real, we would need to know first a couple of things. We would need to know the angle of the ramp. Okay, 30 degrees. We would need to know the speed at which we come off the ramp, 20 meters per second. So our our projected velocity. Our projected velocity is going to be 20 meters per second at 30 degrees above the horizontal. The most important thing for us is how far away do we place the kiddie pool? That's what we have to calculate before we try this thing. Okay, so here's what we have to do. We need to do what we did with the other ones. And we need to break this up into its vertical and horizontal components. The most important piece of information I need is where to put the pool. That is, horizontally, how far will I travel after being launched off the ramp? Okay? Now, the only thing I know is that coming off the ramp, I'm moving at 20 meters per second, 30 degrees above the horizontal. Does that have a vertical and horizontal component? Can I find them?
Yes.
Okay, here's where the vector part comes into these questions. I have to find the x and y components of that projected velocity in exactly the same way we've been doing it for all our vector addition stuff. Okay, so vertically speaking, I need to know what the initial vertical velocity is, which is this side of the triangle. So that's going to mean the sine of 30 times 20 meters per second. Positive 10 meters per second. Why did I put a positive in on this one and I didn't on the others?
Because you're gonna fall back down.
Right, I'm going to go up and down in this one. Okay, so I've got this and I know this. I know one more piece of information. Okay, so I want you to think about what I'm going to show you here. Okay, this is just the vertical part of that motion.
You stop.
How fast is the marker going when it comes back to my hand compared to when I threw it?
Isn't it the same?
It's the same. Okay, if I throw this, when it leaves my hand, if it's moving at 4 meters per second, it slows down at 9.81, gets to a stop, and then falls exactly the same distance back to my hand at 9.81 meters per second squared. When it gets back to my hand, it should be going the same speed it left at.
Initial velocity.
So initial velocity and final velocity are,
The same.
but opposite, right? Okay, one is up, the other is down. Okay, this is the what goes up must come down rule of projectile motion. In a perfect physical world, if the launch point and the impact point are at this are level, VI and VF are equal. Okay, if they're not, then that's not true. Okay, if the 2 points are not level, then it's not true. In this case, they are level, or at least we're going to say that, because it simplifies things a bit. Okay, so I also know then that VF is negative 10 meters per second. All right, so that's the vertical information I have. Can I calculate anything about the horizontal part right now?
Initial velocity?
Well, or constant velocity, actually, yes, because it's only going to have, right, it's going to move at a constant velocity horizontally. And I can calculate that, okay? We just call it V horizontal, okay? And it's going to be the cos of 30 times 20.
You mean 25?
Why would I say 25?
Wasn't the speed 25 meters per second?
Nope, it was 20. Okay, 17.32 meters per second. All right, at this point, that's all I can get for the horizontal part. And I'm looking for the horizontal distance or displacement. What do I need? Time. We're always looking for time, both figuratively and literally. Okay? We're looking for time here because it's the one thing that can go vertically and horizontally. Okay, so can I find the time with my vertical information?
Yes.
Okay, manipulation of our good old science 10 acceleration formula manipulated for time. Right, so we'll have negative 10 minus 10 over negative 9.81. All right, so this thing is in the air for 2.04 seconds. I'm gonna keep all the decimals, I'm just gonna write 2.04 seconds. All right, so I'm gonna bring that over here with my horizontal information. Now, I can calculate how far away I need to put the kiddie pool in order to land safely. Okay. All right, so I'm going to take this number here and multiply it by the horizontal velocity, that number there. All right, I need to put it 35 meters away. That's a long way to travel through the air, off of a slip and slide ramp, with nothing underneath you but hard ground. Okay? Now, there's a lot of different ways a projected at an angle projectile motion question can go. That's one of them, okay? Where I would need to find the horizontal distance traveled, right? I mean, most of the time when you're dealing with a projectile, you're trying to hit a target, so it's usually one of the things we want to calculate, okay? But other things can be, I give you how far it travels horizontally, and I ask you to find the projected velocity. That would be the hypotenuse of the triangle. Okay, you'd have to work backwards from what we just did. Or I ask you to find the maximum height that the object might attain above the ground. Okay, stuff like that. So there's other ways a question like this can go, but fundamentally, this is what it looks like. Okay, you're going to have to find vertical and horizontal components. Okay, you're going to likely have to find time, okay, and use it to calculate something else. All right, Mythbusters busted this one. Okay, and it was like one of their coolest episodes.